Hello, am I audible?
Yes, sir, you're audible.
Okay, so we shall begin then. This is the first of the NPTEL problem solving sessions on the course Design of Power Electronic Converters. The course is instructed by Professor Shabrinath from IIT Guwahati, but as some people are asking in the chat, Professor Shabri won't be joining these sessions. So these sessions are being conducted through NPTEL, but Professor Shabri, I'm not in contact with her. And I will just be going through some problems and summaries of the sessions. And you can clarify your doubts. If you have any doubts, you can ask me during these sessions, or you can ask in the portal, the NPTEL SWAYAM portal. Or if you want to get in contact with Professor Shabri directly, you can email her, but she will not be joining any of these sessions. So if you have any questions, you can ask in the chat, or you can unmute and you can ask on the microphone. And at the end of these sessions, we'll also have a dedicated question and answer session. So in these sessions, we will basically summarize what is being taught during the week, and we will solve some problems which will be similar to the assignment problem, but not exactly the same. So you will get the assignment solutions in the next week after the assignment deadline is over. During these sessions, we will solve similar problems, but not exactly the same. So in the first week, uh, the topics that were covered in the first week are the first lecture basically talked about some applications of power electronics, and then two converters were analyzed in this week, buck converter and a simple edge bridge converter. So in the applications of power electronics, what was mentioned was a diverse group of areas. So first of all, motor drives is a very important application of power electronics, where whether you have to control a DC motor or AC motors, you use power electronics to vary the voltage level, the AC voltage level or DC voltage level, and the AC voltage frequency to control the speed and the torque of the motor drives. And this is done through power electronic converters. Similarly, other applications of power electronics include switch mode power supplies, where we require some fixed DC voltage. Usually it is very low voltage, like 12 volts or 24 volts. And this you have to get from the AC supply, the 230 volt AC, 230 or 240 volt AC supply that you get at your homes. So this conversion from high voltage AC to very low voltage DC, this is done using power electronics. So some examples of these are PSUs, which are power supply units in your personal computers. And similarly in chargers, you give the AC supply and you get very low voltage at the output. Similarly, adapters where you can have at various DC voltage, these adapters are available. Similarly, other applications of power electronics include in servers, where again you need low voltage but very high current applications, and also in inverters, where you have uh, 12 volts or 24 volt batteries and you want to convert them into single phase AC or three phase AC, depending on the application. So this can be used in our homes during for backup supplies. Similarly, UPS for PCs, they also have a battery and then they invert that voltage to AC supply. Another major application nowadays is renewable energy applications, because the renewable energy sources, they don't provide us the power in the form that we want. For example, solar energy, it provides DC voltage, and that voltage is fluctuating. The current is fluctuating dependent on the solar irradiation. So we have to convert that voltage first of all in AC and in a consistent manner. So that is done using some power electronic converters. Similarly, wind, the power generated by wind is also not constant, fluctuating. The power level, the voltage level, these fluctuate depending on the how much wind is available. So to uh, interface these renewable energy applications with our grid, that is at a fixed voltage and a fixed frequency, we need some power electronic converters, or we use some power electronic converters. And electric vehicles are nowadays a very important application of power electronics, because the motors that are used in the electric vehicles are electric motors instead of the combustion engine that is used in petroleum-based vehicles. Electric motors they have to they run on electricity, as the name suggests, and the voltage level, the frequency of the voltage, all these are variable depending on your speed and the load that is in the vehicle. The how much If you want to accelerate, you require more current. If you want to go fast, you the frequency of the voltage has to be high. So these uh, conversions have to be done using a power electronic converter. Similarly, if you want to charge vehicles, so these chargers are slightly different from your uh, mobile phone chargers, because these chargers are very higher voltage depending on the battery voltage, and also very high powers. So all these things are done using power electronic converters. And lastly, the wireless charging, which is a very emerging field for phones and vehicles, this is also done using power electronic converters. So this is the summary of what was mentioned in the lecture. And there are, of course, more applications, but these are some of the major applications of power electronics. Now, if we come to the converter analysis that was done in this week. So first of all, the course is uh, basically it is intended as a second course in power electronics, where you have a basic understanding of power electronics and how it works. But now this course will focus more on the design aspect. So the analysis portion will be just a quick overview. We will not go into very much details of this analysis. And so in this lecture, two basic converters are taken for even in these converters, we will focus on the design aspect at later stages. So during the analysis, we will have some assumptions that we'll follow, and these are mentioned here. So firstly, we have the the first assumption is that we are analyzing these converters in steady state. So that means when the converter starts, it will take some time for the voltage to build up. And similarly, if there is any change in the load, if the load current certainly increases or decreases, then there will be some transients. So we are assuming that we are not dealing with these transients. We are assuming that we have reached the steady state. That means the inductor current is the average of that inductor current is constant. Similarly, the average of the capacitor voltage is constant. And that leads to the inductor volt second balance principle and the capacitor charge balance principle. That means the average voltage across the inductor over a switching cycle is zero. So otherwise, if there was any positive or negative average voltage across the inductor current will rise or it will fall. The average inductor current will either rise or fall. And that we are assuming in steady state, the average inductor current stays constant. So that is why we have the inductor volt second balance principle. And similarly for the capacitor, the charge of the capacitor is no net charge that goes into or out of the capacitor in steady state. So another approximation that we make during this analysis is what is called a small ripple approximation, or sometimes linear ripple approximation. So that means even though the capacitor voltage will have some fluctuation in the voltage, we assume that the fluctuation is so small that we can approximate that voltage to be constant. So this is especially true for capacitor voltages, even though in inductor currents, we'll also make these assumptions sometimes, but the inductor current ripple is usually uh, not that small compared to the capacitor voltage ripple, which we usually take to be quite small, especially in DC-DC converters. And finally, the third assumption that we will make is that we are dealing with ideal circuits. So that means that if we have an inductor, that inductor will not have any resistance. During the first analysis that we do, it will not have any resistance, it will not have any parasitic capacitance. The switches that we will deal with, if the switch is on, then it will not have any forward voltage drop or any resistance while it is on, and when it is off, it will not have any leakage current. So these are the assumptions that we make while we do these analysis. So let's start with the first converter, the buck converter that was taught during this week. So this is the circuit of the buck converter. So we have an input voltage and we want to get another output voltage. And if you must know that the buck converter output voltage, DC voltage, is less than the input voltage. We'll also see that how that comes out to be in the analysis. And we have one control switch here, in this case a MOSFET, and we can supply a gate voltage to this MOSFET for it. When we want it to turn on, we will supply a positive gate voltage, and when we want it to turn off, we can supply a zero or negative voltage. And we have another diode, an inductor, capacitor, and the load resistor. So this basic circuit will have two switching states depending on whether the main control switch, which is the MOSFET, is on or off. So if this switch is if this switch is on, then we get the circuit that is shown in the slide. So this switch will be on for a duration which we call DTS. So TS is the switching frequency, how fast the MOSFET is switching, and D is a fraction of that time. So D is a fraction from 0 to 1, and DTS will be a fraction of the time for which the MOSFET is on. And when the MOSFET is on, the equivalent circuit is shown in the slide. So the inductor will be directly connected to the input voltage. And in this equivalent circuit, we can then find out what are the different voltages and currents in the circuit. So the inductor voltage, the voltage across the inductor in this case, will be the input voltage minus the output voltage. And this, as we'll see, it will V, the inductor voltage, is equal to L di by dt. And we will use this equation to see the inductor current ripple and for the inductor volt second balance. Similarly, the capacitor current, if we see during this interval, is the inductor current minus the output current. The voltage across the main switch is zero because it is on, and here we are using the ideal assumption that there is no voltage drop across the switch. The voltage that the diode is blocking, because the diode is reverse bias in this case, so the voltage that the diode is blocking is the input voltage. So if you see uh, the voltage loop on the left side of the circuit, the voltage that is blocked by the diode is the input voltage. And the current through the switch is the inductor current, and the current through the diode is zero because it is in reverse bias condition. So this is the DTS interval. And the rest of the switching interval, which is called the 1 minus DTS interval, will look like this, as shown on the right side of the slide. So the switch now is off because we have removed the supply from the switch. And because of that, the diode gets forward biased. The inductor will switch voltage, and that leads to the diode being forward biased. And the inductor current continues through the diode. So this analysis we are doing, we are assuming that the converter is in what is called CCM, that is continuous conduction mode. That means the inductor current basically does not go to zero. It does not stop conducting. And during this 1 minus DTS interval, similarly, we can find what is the inductor voltage, what is the capacitor current. The switch in this case is blocking the input voltage, and the diode is conducting the inductor current. So now we can apply the volt second and capacitor charge balance principles. And if we apply those things, we find out that the output voltage is equal to D times the input voltage. So basically, since D is a fraction from 0 to 1, we can understand that the output voltage will be less than the input voltage. It can be between 0 to V at the maximum. And similarly, if we apply the capacitor charge balance principle, we can get that the inductor current, average of the inductor current, is equal to the output current. And we can write the output current using for a resistive load as V out divided by the resistance R. So now we can see some waveforms using this analysis. So on the right side, you can see from the top, we have the gate voltage or the gate signal that is given to the controlled switch, the MOSFET. And so for some fraction of the switching cycle, we provide a positive voltage to the MOSFET so it turns on. And then we remove that voltage, or we provide a negative voltage so that the MOSFET turns off. And when this switch is on, as we see in the first circuit, the voltage across the inductor is V in minus V out. And as we saw, V out is a less than V in, so V in minus V out will be a positive voltage. And when we apply a positive voltage across an inductor, the inductor current will rise using the basic inductor equation, that is VL is equal to L di dt. So the inductor current in this case will rise. And in the next interval, the voltage across the inductor is minus V out, which is a negative voltage, so the inductor current will fall. And in steady state, we assume that if the inductor current starts at a point, then at the end of that, the switching cycle, the inductor current again will reach the same point. So this ripple in the inductor current will be constant. So also we can see that the voltage that is blocked by the diode is during the DTS interval, it is equal to V in. Similarly, the switch also blocks the same voltage, but in the other interval, 1 minus D interval. And the switch carries the inductor current during the D interval, while the diode carries the inductor current during the 1 minus D interval. So now this analysis that we have done so far is for CCM condition, that means continuous conduction mode. So that means the inductor current is always positive throughout the cycle. And as we saw that inductor current is equal, the average inductor current is equal to the output current. Now, if for the same voltage, the output current reduces, so let's say the output resistance increases so that the output current now reduces, then this whole inductor current will basically shift down. It will come down together with the ripple, and a point will reach when the inductor current will start from zero. It will come to a high point and then again go back to zero. And that point is called the boundary condition between CCM and DCM. DCM being the discontinuous conduction mode. If the output current is less than this amount, then the converter will go into DCM. So that means there will be another state between the DTS state and the 1 minus DTS circuit that we saw. There will be another circuit in between that where there is no current through the inductor. So because of the diode, the inductor cannot allow a negative current. So that is why when the inductor current reaches zero, it will stop at zero and the circuit will change to a DCM circuit. And in this week, we have not studied the DCM circuits because in the DCM case, the output voltage equation will change. So we want to limit our analysis to CCM and the boundary condition. We want to ensure that our converter will remain in CCM. So how can we do that? So we can understand that during the boundary condition, the inductor current average will be equal to half of the ripple in the inductor current. Because this is a triangular current and the average of that triangular current is equal to half of this, half of the peak of the triangular current. So the average inductor current during the boundary condition is equal to half of the ripple. Now we can find out an expression for the ripple using the basic inductor equation, that is L delta I divided by delta T is equal to the voltage across the inductor. And if we see in the DTS interval, so the time duration delta T is equal to DTS, and the voltage across the inductor at that time is V in minus V out. So if we put these values in the second equation here, we will get that the delta I in that case will we can find out delta I during from that expression, and then from the first equation we can find the boundary condition, the inductor current value during this boundary condition, and that is given by the last two equations. In the last equation, I have just substituted V out as dV in, so that we get the equation in terms of V in, the duty, the switching time, which we can get from the switching frequency, and the inductor value. And this value of inductor is called the critical value of inductance. Because if the inductance is less than this value, then basically the converter will go into DCM uh, before this value of inductor current. So if we want to have a minimum current, that is ILB, the inductance value must be greater than the L critical value. And we will see that as an example in the problem solving session. So now the critical value defines the condition where where our converter will be in CCM. But in practical cases, we want to choose the inductance value from a condition on the inductor ripple. So that means that in practical cases, you will be specified that the inductor current ripple should not go beyond a percentage of the output current. So based on that, we have to find what should be the value of the inductance. And that also we can do using the same equation. And if we substitute the values of the different terms in this equation for dTs interval and 1 minus dTs interval, we will basically get that uh, the ripple in the inductor current is equal to this value that is shown in the last. And that is irrespective of whether we are in dTs or 1 minus dTs interval, we will get the same expression for the inductor current ripple. And this in the ripple equation we can use to find out the value of the inductance that is required to satisfy a given ripple condition. So now choosing the capacitance value is actually similar, but for the buck converter case is slightly different. So in the buck converter case, how we find the value of the capacitance, first of all, we can see that because of how the circuit looks like. So if we see the circuit here, the inductor is directly connected to the capacitor and the load. And this is true for both the switching intervals. The inductor, this connection does not change. So the capacitor current is always equal to IL minus I out for both the switching intervals. So what that means is the ripple in the inductor current goes through the capacitor because the capacitor provides a low impedance path to the high frequency component of the current, while the DC component goes to the load. So the capacitor current then we can find out will have a shape which is like this shown in the slide. It is just the ripple part of the inductor current. So it is a zero average current, which is only the ripple part of the current. Now, if we want to find out how the voltage across the capacitor then changes because of this ripple current, we can use basically uh, the capacitor equation, charge equation, which is delta Q is equal to C delta V. And we can figure out the delta Q in this case, which will be equal to the area under this, the gray portion that I have highlighted here. And if you find this using the area under this triangle, that will be the charge that goes into the capacitor for Ts by 2 interval. And because of this charge, the capacitor voltage will rise. So this will be the delta V that is across the capacitor. And if we substitute the value of delta IL from the inductor equation in the previous slide, then we will basically get the equation for the voltage ripple across the capacitor in terms of the input voltage, the duty, the switching frequency, and the L and C values. So in this way, we can find out the what is the capacitance that is required to satisfy a minimum voltage ripple condition. So this is basically a summary of the buck converter analysis and the design of choosing the L and C components. Now, the second converter that was studied in the course this week was an H bridge, or also called a full bridge. So basically, in this circuit, we have uh, two legs. In each leg, we have two bidirectional switches. Bidirectional means that they can carry current in both positive as well as negative direction. And in this case, what I've shown here is realized using an IGBT connected with an anti-parallel diode. And in each leg, we have two switches, and we have two legs connected to the same DC voltage supply. And the output is taken from the midpoint of the two legs. And basically, we have one basic rule that the both switches in a leg cannot be on at the same time, because if they're both on, then the input voltage source will be shorted and there will be a huge current through these devices, which will basically damage the devices. So we can not turn both of these switches on at the same time. So that leaves us with four combinations that are possible. So either the diagonal switches are on, so that means TA plus and TB minus are on, is on, while the other two will be off to satisfy the rule that we mentioned. So that is one option. The other option is the other diagonal switches will be on, that is TP plus and TA minus. And then we have two more options where either the top two devices are on or the bottom two devices are on. So these are the four possible combinations. Now, because depending on which of these combinations we are using, we can have two basic modulation techniques. So, okay, before that, we can just see the equivalent circuits for the four states that we mentioned. I will just show for two states because the other two are quite similar. So if the diagonal switches are on TB plus and TA minus, this is how the equivalent circuit will look like. And we can see in this case, the output voltage is equal to the negative of the DC voltage. And the DC current, IDC, based on how it is defined, it will be equal to the negative of the output current in this case. And if the output current is positive, then the diode of DA minus and DB plus, these two will conduct. So if the output current is positive, you can see that it will be DB plus, and then it will come from the source to DA minus, and then again back to the load. And if the output current is negative, then the IGBTs will conduct. So it will be TB plus and TA minus. And the voltage that is blocked by the non-conducting devices will be VDC. So if you see, because TA minus is on, the voltage that comes across TA plus will be VDC. Similarly for TB minus as well. So this is one example of where the diagonal switches are on. Now, if the top two switches are on, this is how the circuit will look like. And what is interesting in this case is that the output voltage is zero, and the input DC current is also zero. So this can be understood as a zero state where the output voltage is zero and the input does not supply any current during this state. And similarly, we can find out which devices are conducting, based on whether the output current is positive or negative. And the voltage that is blocked in all cases is VDC. So the voltage that is blocked in both of these cases will be VDC. Okay, someone is asking to solve the circuit for the buck boost converter. So I believe that is the assignment. So I cannot give you the solution to the assignment, but the circuit analysis I think is given in a PDF in the assignment question. So after this H bridge analysis, we will solve the boost converter circuit, but not the buck boost converter circuit because that is part of your assignment that you have to complete during this week. So, as we mentioned, there are two basic modulation techniques. One is called bipolar modulation. So, here what we do is uh, the way we generate the gating pulses for these four control switches is that we have a high frequency carrier wave, which in this case we have a triangular carrier signal, and then we have another voltage signal uh, that we compare with this carrier. Yes, so someone is asking about the presentation. It will be provided. So this lecture is being recorded. The video will also be provided to you, and the PPT will be provided separately. So uh, the way the pulses are generated for the different control devices in bipolar PWM is that we have a high frequency carrier, the triangular carrier, which goes from 0 to 1, let's say, and then back to 0 in one switching cycle. And then we have a reference waveform. So here I've shown a basic constant reference waveform just to show how this will work. When the reference is greater than the carrier, during that time we turn on the switches TA plus and TB minus. So the diagonal switches we turn on. So in that case, the output voltage will be plus VTC, as we saw previously. And if we have an inductive load, then the output current during that time will rise. And as we saw previously, when these two diagonal switches are on, the DC current will be equal to the output current. And then when the voltage, the reference waveform is less than the carrier, we will have another condition where the other two diagonal switches will be on. So TA minus and TB plus. And during this case, the output voltage is equal to minus VDC. And because we are applying a negative voltage to the inductive load, the output current will fall. And the input DC current in that case will be equal to minus of the output current. So it will be a negative current. And then again, the same thing will continue. We will again have the plus VTC interval, and the output current will again rise, and the DC current will again be equal to plus I out. So this is how basically a bipolar modulation works. It is called bipolar because the output voltage varies between plus VDC and minus VDC. So both polarities are included in each switching cycle. So now, if we want to find out what is the average output voltage, we can basically see that for some duration, which we call, let's say, DTS, the output voltage that is applied is VTC. And for the rest of the cycle, which is 1 minus DTS, the output voltage that is applied is minus VDC. And D in this case is basically the value of our reference voltage, of the reference signal. Because we are varying the carrier from 0 to 1, if the reference varies, if the reference is 0, then we will have the DTS terminal will be, interval will be 0. And if the reference VREF is 1, it is at the top of the carrier, then we will have the full DTS will be equal to TS. So basically VREF is equal to our duty D in this case. And if we find the average of the output voltage, which is given here as V out bar, we can see that V out bar is equal to VDC times 2D minus 1. And based on this equation, we can find what the value of D will be, which in this case, as I said, that in this case, D is equal to VREF. So someone is asking that the load is grid connected. How active power flow will flow from DC supply and reactive power flow. Okay, so a grid connected application, it is a bit complicated. We would have a filter here that will filter out some of the high frequency harmonics, and then we will have the grid connected connection here, and then we have to basically figure out what we have to synchronize with the grid, and then develop a voltage which will be slightly, the phase of that voltage will be slightly different from the grid voltage so that we can feed power. So that is an advanced topic here, but that will not be covered in this course, I think. So you may consult some books for that case. Grid connection is a very important topic, but that is beyond the scope of this presentation. So I was talking about the average output in this case. So once we have found the average output, now let's say we want to have a sinusoidal output in order to, basically, if we want to drive a sinusoidal motor, or we want to provide as an inverted sine voltage to our homes using an inverter. So that means in an average sense, the voltage should follow a sine wave with a peak of V out hat. So then we can substitute V out hat, V out bar in this equation, and this will be how our reference voltage waveform will look like. So it will have a DC shift of 1 by 2, and then it will be a sine wave. So that is basically shown here. We have the voltage, the VREF waveform is varying in a sinusoidal fashion. And what that will give us, that the output voltage, the pulse duration of the output voltage will now vary in this sinusoidal fashion. So the pulse duration first is small, and then as VREF goes to the peak, the pulse width increases, and then again in a sinusoidal fashion, the pulse width uh, reduces, and then it becomes more negative. So that means if you find the average of this voltage, the average over a high frequency switching cycle, you will get this dashed voltage waveform. So you get a sinusoidal voltage. And then we can define the uh, modulation index, which is defined as V out hat divided by VDC. And this modulation index we can use to find out what is the minimum DC voltage required for a particular output voltage. Because normally, especially for single phase edge bridge converter, the maximum MA that we get in what is called linear modulation region is 1. And so that means if you want an output voltage which has a maximum output of V hat, you need a DC voltage which is at least equal to V hat. So if we want an output voltage which goes to 300 volts, then you need a DC voltage that is at least 300 volts or more. So that was about bipolar PWM. And we can also see how the output voltage, output current waveform, and the input DC voltage, DC current waveform will look like for a sinusoidal output. And basically, what we can see is that when the output voltage is positive, the inductive load current will rise, and then when it is negative, the load current will fall. And that leads to a current which has a sinusoidal average shape, but it also has a high frequency ripple on top of that sinusoid. And similarly, we can then find out what the DC current will look like, because when the output voltage is plus VDC, IDC will be equal to the I out. And when the output voltage is minus VDC, IDC will be equal to minus I out. So if you follow that, the output current in that way, you will get a DC current which looks like what is shown in the slide. And it has both positive as well as negative portions. But if you find the average of this current, it will be a DC positive average current, a positive DC average current. And besides this positive DC average, it also has a, a switching component, or an AC component, which is at twice the fundamental frequency. And this we can see from if we equate the input and output powers. Because if we assume that the average output is a sinusoid, and the output current is also a sinusoidal current with some phase difference from the input current, the output voltage, And then if we equate the input power, which is the DC power, VDC times IDC average, equal to V out average times I out average. And if we equate these and we do some trigonometry, we will have a constant term, which is the IDC hat that I have shown. And we will also have a uh, an AC term, which is at twice the fundamental frequency. And that is because single phase AC power is not constant. It has fluctuations at twice the AC frequency, and that is reflected then in the DC current. And that has some implications for designing the input capacitance of this edge bridge converter. So this was about bipolar PWM. Then another type of modulation that we have is what is called unipolar modulation. And in this case, it is a slightly more complicated because we have the same carrier, but we now have two reference waveforms to compare with this carrier. VA reference will give us the switching signals for the first leg, that is leg A, and VB ref will give us the switching signals for leg B. And how VA and VB are related between themselves is that if VB is basically equal to 1 minus VARF. So whatever the value of VARF, VB ref will be equal to 1 minus that value. So then we can find out how the node voltages will look like, which is VA with respect to the term the node N. So whenever TA plus is on, the VAN voltage will be equal to VDC, and when TA minus is on, the VAN voltage will be equal to 0. And similar is the case for VBN. When the top device of that leg is on, the voltage VBN will be equal to VDC, and then when the bottom device is on, it will be equal to 0. And once we find the VA and VBN, we can subtract these to find out the output voltage. So in this case, the output voltage varies between VDC and 0 only. It does not go to negative for the case that I've shown here. And that is why it is called unipolar. So because of this case, the output current waveform is also shown here. And what is important here is that DC current varies between plus output voltage and 0. It does not go to negative portion uh, for the case that I have shown here. For a sinusoidal case, it will go to negative as well in the negative half cycle. So that we can also find out later. But now, similar to the bipolar case, if we want to find out what will be the value of VARF and VBRF, we can again find the average output voltage, and based on the average output voltage, we can see what VARF and VBRF will look like. And again, if we want a sinusoidal waveform, we can substitute V out bar using a sinusoidal function. And in that case, this is how the waveforms will look like. So VB ref will be 180 degree out of phase with VA ref. And so VAN and VBN are shown here. And if we subtract VAN and VBN, we will get the output voltage. So in the positive half cycle, the output voltage varies between VDC and 0. And in the negative half cycle, it varies between 0 and minus VDC. And then we can similarly find out the output current as well as the DC current. And it will have the same constant DC part as well as a second harmonic portion. So the difference between bipolar and unipolar is even though unipolar is slightly more complex than bipolar to implement because of having two reference waveforms and then comparisons, the associated comparisons. But that complexity, especially nowadays in digital electronics, is not very hard. But the advantages that we get from unipolar are make it the preferable modulation technique. So the advantages that we get, first of all, is that in bipolar case, the voltage varies between plus VDC and minus VDC. While in the unipolar case, the voltage variation is only VDC. So, so there is a improvement in the transition from twice VDC to only VDC. And that has some implications for the insulation of the load as well as the electromagnetic interference that this switching will generate. And it is preferable that we have a lower voltage transition. So that is why unipolar has an advantage in this case. Another aspect that we can find out is that in unipolar case, the output voltages and currents, the high frequency component is at twice the switching frequency. So even though both the unipolar and bipolar case, if we switch both of them at a switching frequency of Fs, for the unipolar case, the output voltage and the output current, the switching component will come out at twice the switching frequency. And that means we will require a smaller filter to filter out the harmonic components. And lastly, the ripple in the output current as well as the DC current is smaller in case of unipolar modulation. So that means unipolar is advantages for these three aspects. But as I mentioned, it is slightly more complex to implement, but nowadays that complexity is not very difficult. So, so after this summary of the what was taught in the week, we can now come to a problem solving session. The It is quite similar to what you have in your assignment, but instead of a buck boost converter here, we have a boost converter. And I think before we start this session, we can actually have a small, short 5 minute break. So after the 5 minute break, we will continue uh, with this problem. Okay, so we will meet again at start again at 3:57. Okay, so we can continue now. So there is a question in the chat about the ripple in the DC current for the edge bridge inverter. So the question is asking who will supply this ripple current. So yeah, as you can see, there is a high frequency ripple as well as a, second harmonic ripple in the capacitor in the DC input current. So what is usually done in these converters is we will have an input capacitor here. So across in parallel with the DC supply, we will have a capacitor which is actually connected very close to the switches. So this capacitor is supposed to provide the high frequency ripple, and we can also have a very other large capacitors to supply the low frequency, the fundamental second harmonic ripple. And the idea is to have these capacitors which will filter out the the AC component of the current, and they will provide this current while the DC battery or the DC source, it will only provide the DC portion of the current. But in practice, you will the capacitor will not be able to filter out the current completely. So the DC current will not, the battery current will not be pure DC. It will have some AC components. But basically, the capacitor is used to provide these ripple portion of the current. So now we can come to the problem, which is asking about designing a boost converter. So a boost converter, in this case, the specifications are given that we have an input voltage of 30 volts, the output voltage is 75 volts, and the maximum output power is 300 watt. And the maximum ripple in the output voltage is 0.1% of V out. So that will be 0.1% of this 75 volts. And as you can see, it is very small, this ripple in the output voltage. And that is why we use this small ripple approximation, especially for capacitor voltages. Then the question asks us that the boost converter should remain in CCM for the load range of 150 watt to 300 watt. So as we saw for the buck case as well, as the load current reduces, uh, the chances of going to DCM increase because we are getting closer and closer to DCM. So that is why we are asked that the converter should remain in CCM for a load range. Because if we go to very low load, that is less than 150 watt, then it may go into DCM, but we want to stay in CCM for 150 to 300 watt range. And the next specification is that the maximum ripple allowed in the inductor current is limited to 15% of the load current I out. And the switching frequency is 50 kilohertz. So let us first see the boost converter circuit, how it looks like. So here we have the circuit. I mean, it has the same basic components as the buck converter, but they're arranged differently. So here the inductor is connected to the input side instead of the output side, and the control switch is connected between the inductor and the common ground. And then we have a diode again for the freewheeling the inductor current. So again, if we do the CCM analysis, we can have uh, two possible states that are shown here. If so, and a question is asking why ripple in the inductor current is limited. So that basically depends on the application. There are some applications where you don't want to have a large uh, AC component in the DC current. So, so it depends. So, for example, in grid connected applications, you don't want to have a large ripple in the current that you feed to the grid or take from the grid, because that will basically distort the grid voltages. Similarly, for some battery where you don't want to the battery to supply the AC current because that may lead to more losses in the battery. So that is why we will have a specification to limit the ripple in the inductor current. So in these two equivalent circuits, we can see that on the left circuit, the main switch is on, so the inductor voltage will be equal to V in, and on the right circuit, the main switch is off, so the diode will turn on, and the voltage across the inductor will be V in minus V out. And we can also find the capacitor current in these two cases. For uh, the DTS interval, when the main switch is on, the capacitor current is equal to minus I out, and in the 1 minus DTS interval, when the main switch is off, the capacitor current will be equal to IL minus I out. And uh, all these expressions are written here, and we can also find out what is the voltage across the switch, what is the current through the switch, and the diode, the voltage and current of the diode as well. And these are all provided here. And using the voltages across the inductor and uh, the current through the capacitor, we can again apply the volt-second balance principle and the capacitor charge principle to find out the average value of the output current and the average value of the inductor current. And if you do that averaging, you will get that the output voltage is equal to V in minus divided by 1 minus D. So basically what we do is we take the voltage across the inductor during the D terminal, DTS interval, which is V in, and we multiply it by D, and then we sum what is the voltage across the inductor in the 1 minus DTS interval, which is V in minus V out, and we multiply this whole thing by 1 minus D. And the summation of this will be equal to 0, because the average voltage across the inductor should be 0 in steady state. And when we rearrange this equation, we will get the output voltage is equal to Vn divided by 1 minus D. And since D varies between 0 and 1, so that means the output voltage will be greater than the input voltage. And that is the output voltage of the boost converter. And similarly, we can find out the inductor current average expression using the charge balance principle. And in the same way as we did for the voltage, we can find out that the inductor current is equal to I out divided by 1 minus D. And I out in this case will be equal to the output voltage divided by the resistance R. So once we have these things, we can then look at the different waveforms. So the waveforms are quite similar to the buck converter, but the actual values will depend on the specifications that are provided. In this case, the inductor, the voltage across the inductor in DTS interval is V in, and since V in is positive, the inductor current will rise. In 1 minus DTS interval, the voltage across the inductor is V in minus V out, and since we know that V out is greater than V in, so V in minus V out will be a negative quantity. So that is why the inductor current will fall. So then we can also see the waveforms of the switch, how the switch current looks like and how the switch voltage looks like. And if we see, when the main switch is off, the voltage that is across the control switch is the output voltage. If you see the voltage loop on the right side of the circuit, you can see that the V switch is equal to V out. Similarly, when the diode is off, the voltage that is blocked by the diode is the output voltage. So if we have so in the case that is shown here, the input voltage is 30 volt and the output voltage is 75 volt, then both the diode and the switch have to block a voltage that is equal to 75 volt. And for the boost converter, what is interesting is that the diode is always connected to the output. So if we want to find out the average output current, we can see that if we find the nodal equation for this node, which it will be equal to ID is equal to I out plus IC. And if we average this equation, since the capacitor does not take any average current, the average current through the capacitor is zero, so ID average will be equal to I out. So, so that is what I have shown here. The average current through the diode is equal to the average output current. We can also see the current through the capacitor during the DTS interval. The current through the capacitor is equal to minus I out, and in the 1 minus DTS interval, the current through the capacitor is equal to IL minus I out. And in the DTS interval, the current is negative, so the voltage will fall. And in the next interval, the voltage and the current is positive, so the voltage will rise based on the capacitor equation. Now, what the question is asking us, it is similar to the assignment question that you have been given, is what is the voltage rating of these three components, the MOSFET, the diode, and the capacitor. And as we saw previously, the voltage that is blocked by the switch as well as the diode is V out. So since we are given the output voltage is equal to 75 volts, the voltage that will be blocked by these two devices will be equal to 75 volts. And similarly, the capacitor actually also, the voltage rating of the capacitor will also be 75 volts, but we can actually be more precise here if we say that the uh, capacitor voltage will have an average and it will also have a ripple component. And we are given that the ripple is equal to 0.1% of V out. So if we use that specification, we can see that the maximum capacitor voltage, that is the peak capacitor voltage, will be equal to V out plus half of that ripple, because the ripple will go below the average as well as above the average, and the average will be exactly in the middle of this ripple. So that is why the capacitor peak voltage will be equal to V out plus half of that ripple, and V out is 75 volt and the ripple will be 0.1% of 75. So if you do this sum, you will get 75.035 volts. And since we are given that we have to round out for up to two decimal places, so the answer will be 75.04 volts. So there's a question in the chat that in the boost converter, by default, the load is always connected to the source via inductor and diode when the converter is not supplied with the gate sticks. How to avoid this situation? Yes, so the starting of the boost converter is a bit more complicated than the buck converter. Usually what people do is you can have another switch that connects the converter and the source, or you can have what is called as a thermistor, which basically provides uh, very high resistance when the temperature of this thermistor is low, and as it draws more current, the temperature rises and the resistance decreases. But basically, you will need some other circuit component if you want to avoid this condition. So the next question here is that based on the limit on the current ripple, we are asked for the current rating of the MOSFET, the diode, and the inductor. So we can apply a similar analysis that we did previously. So we see that the current rating of the switch will be equal to peak current, peak inductor current. Similarly, the current rating of the diode will also be equal to the peak inductor current. And we saw that the inductor current value, or the expression for the inductor current, is I out divided by 1 minus t. And we can find out the duty from the output voltage, because we know the input voltage and the output voltage. We can find out what the duty will be, and we can then find out the inductor current. And then we are told that the inductor current ripple should not be greater than 15% of the output current. So using all these facts, we can actually find out what is the inductor current peak value. So it will be equal to the average inductor current plus half of the inductor current ripple. As we saw, the average inductor current is I out divided by 1 minus D. And then we had 15% of I out divided by 2. And I out here will be equal to uh, 300 watt divided by 75 volts. That will give you the output current, which in this case is 4 amperes. And the duty in this case is zero point 0.6 because the output voltage is 75 volts and the input voltage is 30 volts. If you find out the duty from the boost converter voltage equation, you will get that the inductor current average is 10 amperes, and then the ripple has to be uh, zero point 0.6 uh, amperes, and half of that is 0.3 amperes. So the answer to this question is basically the peak inductor current, which is 10.3 amperes. So all of these, the MOSFET, the diode, and the inductor, the current rating of all of these will be 10.3 amperes. So the next question is asking about what is the value of L critical. And we are told that we have to consider the entire load range given for CCM. So that is from 150 watt to 300 watt. So L critical is basically the value of the inductance which is needed, the minimum value of inductance that is needed to avoid going to DCM. So for if we have this inductance, then we will go to the boundary condition. So as we saw in the buck converter case, as the output current reduces, we go closer and closer to DCM. So the condition where we are most likely to go into DCM is when the output current is the minimum. So that is why we will take the minimum power to calculate the value of the critical inductance. So that is the boundary condition, the boundary output current will be equal to minimum output power divided by the output voltage, which is 75. So that will give us the uh, boundary output current. And then we can see that during the boundary case, the inductor current average is equal to half of the inductor current ripple. So that is true for buck converter, boost converter, buck boost converter in all cases. In the boundary condition, the average inductor current is equal to half of the peak to peak ripple in the inductor current. And since we know for a boost converter, the inductor current is equal to I out divided by 1 minus D, it will be same in the boundary case as well. ILB, which is the boundary inductor current, will be equal to the boundary output current divided by 1 minus D. And D is constant at 0.6 for all these cases because the output voltage is constant at 75 volts. So from this expression, we can find out the value of the peak-to-peak ripple in the inductor current. And then we can basically use the inductor current expression, the LDIDT, to find out the expression for the ripple in terms of V in D switching frequency and the inductance. And if we equate these two expressions for the inductor current ripple, by equating these two, we can then find the expression for the critical inductance, which will be given by V in into D divided by twice the boundary output current into the switching frequency. And we know the input voltage, which is 30 volts. The duty is same as 0.6 because the output voltage is 75 volts. The boundary output current we can find out using the minimum power, and then the switching frequency is given at 50 kilohertz. And if we substitute all these values, we get that the critical inductance is equal to 36 microhenry. So the answer to this question is 36 basically. So the value, the unit is already given. We have to give the value of the inductor, the inductance in microhenries. So this is same for you in the assignment as well. You don't have to write the value in the text box. You only have to write the number. which will be the unit is provided in the question itself, microhenry. So the answer will be 36. So next, the question is asking about the value of the ripple inductance in microhenries again. And again, we are told that we have to consider the entire load range for the CCM. So the L ripple is basically that value of inductance which satisfies the ripple condition. So we are told that the inductor current ripple should not be more than 15% of the output current. So so that means the inductance has to be of such a value that will satisfy this condition. So again, if we see the how we can find the value of the uh, L ripple, we can basically see the different terminals and different intervals and what is the voltage across the inductor and what is the duration of that interval. So for example, in the DTS interval, the delta T will be equal to DTS and VL will be equal to Vin. And if we rearrange these quantities, we can get that L ripple is equal to Vin into D divided by the ripple in the inductor current peak to peak ripple times the switching frequency. And then now we have to see what is the condition in the ripple. So because we are told we have to consider the entire range of the CCM, which is from 150 watt to 300 watt, we have to see that the delta I should not be more than 15% of the load current. And so we can do basically at the two ends, at 150 watt and what is the case at 300 watt. And we will get basically that the L ripple requirement is more at 150 watt than it is at 300 watt. So if we want to satisfy the requirement in all the cases, then we will take the greater of the L ripple requirement. So that is why we will take the minimum output current, which will be basically the condition for 150 watt, and 15% of that current, if you find out, it will be zero point 0.3 amperes. And then if you substitute this value of delta I in the L ripple expression, you will get 1.2 millihenries. And since we are asked to write the value in microhenries, it will be 1200 microhenries. So the answer to this question is 1200 microhenry, which is the value of the inductance, the minimum inductance required to satisfy the ripple condition. And so this also tells us that even though the critical inductance was only 36 micro, but to satisfy this ripple requirement, we have to use a much, much larger inductance, which is 1200 micro. So usually the ripple requirement is much more strict compared to uh, the CCM requirement or the critical inductance. So, and finally, the last question is a multiple choice question is based on the above calculations, which of these following inductance value you'll choose? So, it's a very simple question. So, I think most of you can guess what is the answer. So, if those who have understood this question, they can write their guesses in the chat, what they think should be the answer. So we just find out that the value of L ripple is 1200 micro. So based on these four options, what should be the value of L that we should choose? Yes, so basically the inductance value should be at least 1200 micro. So anything more than 1200 micro we can choose. So the answer to this last problem is D, 1275 micro. That is out of these four, that is the best option. So these are all the problems that we had, and the assignment that you have is quite similar to this, and you have also been given a document which has the analysis of the buck-boost converter. So you can use this session and the analysis of the buck boost converter to find out the answers to those the assignment that you are given. So if anyone has any more questions, you can ask in the chat or you can unmute and ask on the microphone as well. Can you explain full bridge without carrier frequency, simple PWM with deadband? Without carrier frequency, yeah, you can give a simple duty to the edge bridge, but it depends on which switches you are turning on of the edge bridge. And based on which switches you are turning on, you can find out the output, the average output, uh, just like here you are finding out. But with deadband is actually very small compared to the switching cycle, so it does not affect the output voltages in a major fashion. So while doing the analysis, we actually ignore the deadband. But can you elaborate what you mean without carrier frequency? Because this is the simplest way to yeah, do the modulation of edge bridge. Because even in a buck converter or a boost converter, when you practically implement it, you will have a carrier. You will have a triangular or a sawtooth carrier, and then you will compare your duty with that carrier to get the PWM. So the carrier is one of the simplest ways we use to generate the PWM. So either we have an analog case where we have a sawtooth generator or a triangular waveform generator, then we have uh, a controller that will produce a control voltage, and then we have a comparator which will compare. Or in the digital case as well, we have counters that will count from zero to uh, uh, some uh, uh, some high value and then go back to zero. So we always use a carrier and then we compare with with a reference waveform. So I hope that answers the question. Any other questions? So assume HVAC supplies an RL load, then how the reactive power supplied from the battery. So basically what will happen because of we see the power equation. Uh, Basically when there is more reactive power, then there will be more of the switching, the AC component in the DC, and that's the same the equation that we saw here that will be followed. Because if there is more reactive power, then this phase angle phi will increase, and that will change basically the DC component as well as the AC component. But again, depending on how much capacitance you have and how much you allow the battery to supply the AC portion of the current, uh, then the battery will supply the current in that fashion. And if there is more reactive power, then we'll probably need a larger value of capacitance to handle the power oscillations. So is that clear or do you need more clarification? So my email ID I will write in the chat. If anybody has any questions, they can ask me there. So it is basically uh, salehkn@gmail.com. The rating of the inverter in terms of kVA. So yeah, that depends on the uh, the output voltage and the output current, the maximum output current. So once you have the output current, that output voltage that you want, and based on what load is there is, if you have the output current, then uh, you can just multiply the RMS voltages and current to get the kVA rating. But that will not the ratings of the devices and the capacitors, that is a bit different, and that will be covered in the course actually. So because the course is on the design of these converters, so the course will cover how to actually select what is the voltage rating of uh, the switch to select, what is the current rating of the switch to select, and how the losses are calculated and how the heat sink is calculated. But the basic rating is will be just simply the voltage and current of the output that is required. But we may want to have some safety factor. So that depends on the application. If you are expecting any fluctuations in the output, in the input, so in that case, you can have a safety factor. So even though the output voltage and current is only, let's say, X amount, you can have 1.5x times the inverter rating for so in case there is any extra load for some duration, the inverter should be able to handle it. But that depends on the particular application and the different cases for which the inverter will be used. How to choose the switching frequency? Yes, so ideally we would like to have as high switching frequency as possible because that reduces the requirement of the filter size. But practically, the switching frequency leads to more losses in the switching devices because we were assuming in this analysis that our devices are ideal, but practically, whenever the devices turn on and off, they will have some losses associated with them. So, and those losses which will lead to more heat, and uh, if the switching frequency is too high, then the devices will generate too much heat and they can get damaged. So the switching frequencies actually depends on how much losses you can sustain, how big of a heat sink do you have, uh, and what is the requirement if of the size of the converter. If you can have, if you are allowed to have a very large converter, then you can have low switching frequency because the filter size can be large. You don't have any problem. But if you want to have a very compact converter, then you need to have high switching frequency so that the filter size is reduced. But then you have to manage the heat in a proper way. You may have to use the silicon carbide or gallium nitride devices or you may have to do some liquid cooling or some soft switching techniques. So a lot of factors come into the switching frequency, but it is basically a trade-off between uh, the efficiency or losses versus the filter size. And depending on what you can allow, you have to choose the switching frequency in that way. Uh, Minimum rating on boost converter in CCM mode. Uh, minimum rating, minimum rating for what? The switches, the inductor. What exactly are you talking about? The minimum rating. Yes, so the minimum rating is for CCM because as we saw, uh, whenever the output current reduces, we are more likely to go into DCM, and that is true for all for all of these basic DC-DC converters, buck converter, boost converter, buck boost converter. Whenever the output current reduces, the average inductor current will also reduce, and if the depending on how high the ripple is, it will come closer and closer to the boundary, and then it can go into DCM. So that is true for all these converters, and that is because of this situation. And the DCM arises because the diodes are not able to carry negative current. But there are some converters where instead of having uh, this diode here, we can have another MOSFET here. And in that case, we can actually, there is no DCM. The current can go negative and the converter can still operate. And there we will not need this minimum rating, power rating. But basically, this power rating is to avoid DCM condition. No, we can use for the boost converter for less than 150 watt, but it will go into DCM mode. And in DCM, the output voltage expression changes slightly. It depends. It becomes dependent on the inductance, the load, resistance, and the duty as well. So we can, but still we can use the boost converter for less than 150 watt, but in DCM mode. But also, so if you see that the critical inductance that we found was only 36 micro, but what we actually ended up selecting was 1200 micro. So that means we can actually go for less than 150 watt and it will not even go into DCM because we have a much higher inductance. So it will probably, it can go for much lower power without going into DCM. So there is no problem uh, inherently with 150 watt. It just depends on the values of the inductance and the load current that you have. Okay, so the session is basically over. If you have any more questions, I will still be here for some time. But those uh, who want to leave, they can leave. 230 volt AC supply, so I can drive three phase. Okay, so usually if you want non-isolated case, what can be done is you can have a boost PFC in the input stage. So that will produce a DC voltage that is uh, higher than 415 volt peak, which is like 600 volt around. And then you can use a three-phase VSI to generate the three-phase voltages for the induction motor. So there are a lot of options, but this is, I think, the simplest way. So uh, first have a boost PFC, which is you have a rectifier and then a boost converter, and then it will produce a DC voltage, and then you can have a inverter. But again, so it is single phase power, which is not constant power. It has uh, second harmonic fluctuations, and the three phase power is a constant power. So you will need a large DC bus between the boost converter and the three phase inverter. Resonance converter, I don't think, because this course is dealing with the design aspects. They are not dealing with different topologies and different PWM methods. So I don't think resonance converter is covered. So you can actually see all the lectures on YouTube. You just search for design of power electronic converters by Professor Shabarinath, and you will see all the lectures in the NPTEL channel. So you can see all those what the topics that will be taught. But I don't think the resonance converter is there. Yeah, PFC is not a requirement. It depends on if you want to uh, have unity power factor, because otherwise you will draw uh, non-unity power factor as well. You will draw some additional current, which can lead to more losses. So PFC is not a requirement, but I was just suggesting what is commonly used. So if nobody has any questions, then I think we can end the session for today. So thank you all for joining, those who were able to join. And as I mentioned, this lecture is recorded and it will be available. Uh, the recording will be made available to you, and the presentation in PDF format will also be made available to you. Okay, so single phase to three phase and DC bus capacitor size. Basically, a single phase power is not constant. It has second harmonic fluctuations that we also saw in the H bridge case. So basically, yeah. So if you see, it's the single phase power. It will have a DC component or a constant component and then a variable component, just like IDC here. But three phase power, if you see, if you multiply all the three phase powers, three instantaneous three phase voltages and currents, you will get a constant power, which is uh, like three three times V phase I phase into uh, the cosine of the power factor or cosine of the phase angle, and that is a constant power. So if you are converting from single phase to three phase or single phase to DC, this the power fluctuation has to be managed somehow, and usually that is done using the DC bus capacitor, or here the H bridge input capacitor, DC side capacitor, and that is usually that requires a very high capacitance because of that fluctuating second harmonic. And there are different methods to reduce the capacitor size, but that is beyond this the scope of this presentation. Reference, you can search what is called active power decoupling. If you search that on Google Scholar or something, you can find many references which are trying to uh, reduce the capacitor size, and they will probably cite some previous references as well. So it is called active power decoupling. So I will write in the chat as well. So if you see what they are trying to do in active power decoupling, you will also understand the problem itself. The problem is that single phase AC power is not constant, and that requires high capacitance values. And how to reduce this capacitance values is the concept of active power decoupling. Okay, so if that is all, then we can end the session for today. Thank you all for joining. I will see you next week, those who can attend. Thank you all. Goodbye.